Okay, so when we were in here last time, we were talking about moments and center of mass, and we went from one-dimensional, which is this, to two-dimensional, which is this, and now what we're going to do is we're still going to be working in 2D, but the shapes are going to be, you're actually going to have a region, okay? So we're going to go back and talk about being bounded by certain graphs, kind of like what we did in 6.1. And if you notice the mass of a lamina, and I'll explain what lamina is in a minute, but if you look at the formula for the mass of a lamina, that is your area formula from 6.1. So we are going to use that again, and then we're going to do some of the other formulas. This is a lot of algebra, more so than anything. So you got to kind of be brushed up on your algebra a little bit. One thing that I do want to point out, I think it's this way on your formula page, correct me if I'm wrong, it should be anyway, is when you look at these formulas in particular, pray tell they're on there, yes. Should be on the back side. Are they on your formulas page? Check and make sure. Yes. Okay. On your formulas page, I want you to notice these are the formulas for finding a centroid or finding well, we'll use these to find the centroid. But to find the mass and the moments, these are the formulas. And if you'll notice, it's a little bit different on your page and the ones in the book. And I'm just going to save you a little bit of headache because the formulas in the book and the formulas on this page, it has a Greek letter called rho. When we talk about this particular section, when you talk about moments and centers of mass of a homogeneous or homogeneous, however you want to say it, lamina, density does not matter. Because we're not talking about any type of pressure. We're not talking about any type of force. What we're just trying to do is trying to find the center, the fulcrum, like we talked about last time. So the reason why these formulas don't have rho on there is because when you do x bar and y bar like we did last week, rho cancels out. It's density. And so when you have the exact same density in m sub x as you do in m, when you get down to do x bar or y bar, they're two rows, the two densities, they cancel each other out. So I just saved you a little bit of time, and you can put it on your formulas page if you want to. You can just go ahead and mark the rho, the Greek alphabet, the Greek letter rho. You can go ahead and mark that off if you want to. Okay, so if you're wondering why I don't have rho in these formulas, and when we start working these problems we won't use rho either, the reason being is because in the end when you do x bar, y bar, the rho cancels out anyway. So I just say eliminate it in the beginning. So it is going to be a little bit different from the formulas on your page and on the formulas on your in your book. So again, on your formulas page, in this particular area only, mark off rho. Because if you go on down to fluids, you'll see rho again. Density does matter there. Okay, but density does not matter here. And that's what rho is going to stand for. All night tonight when we talk about rho, just understand we are talking about density. Okay, so going back to this word lamina. What is a lamina? Lamina is nothing more than a cutout. Okay, like in geometry, if you have a poster board and you make a shape on that poster board and you cut it out, you've made a lamina. Okay, so what we're trying to do is we're trying to find a centroid or the fulcrum or the balance point of a lamina, which is just a shaded region. You've dealt with the shaded regions in the beginning of chapter 6. It's the exact same thing. Okay? Homogeneous or homogeneous means that the density is the same throughout, and that's why the density rho cancels out. All right, so what are we going to do here? Well, in order to find the centroid, again, your centroid, like we talked last week, your centroid is x bar, y bar. So x bar is going to be m sub y over m, and y bar is going to be m sub x over m. Now, little m stands for your mass, okay, and big M stands for your moment. So, in order to find mass, you're going to have to find all three of these. You're going to have to find little m, m sub x, and m sub y. So whatever your system is, if you want to just, this is what I do, I just go down through there and check them all. Okay. So to find little m, again, it's just the area to find mass. It's just the area formula that you use in 6.1. So we're going to integrate from a to b, f of x minus g of x, d of x. Basically, you're going to integrate using x boundaries, which means you're going to do top minus bottom. Okay? X boundaries, and then top minus bottom. So for m sub x, and this, if you didn't have a formula page, this would just be something that you would have to memorize. Okay, all these formulas have been derived. If you want to go in and look at the proofs, you can. They're in your book. But m sub x is going to be the integral from a to b. The boundaries are not going to change. And then you're going to do 1/2, and this is where the algebra comes into play. You're going to do f of x plus g of x times f of x minus g of x. What does that look like to you? Kind of like a sum and difference, right? And so when you fold this out, the middle two kind of go away, and you get the difference of two squares. Same thing. Okay, m sub y. Boundaries, again, are not going to change, but then you're going to do x, which is kind of your radius, so you'll have x times f of x minus g of x dx. All right, and then we're going to use all three of these, just like we did last week, in order to find x bar, y bar. X bar, again, like I said, is m sub y over m, your moment of y over your mass, and then your y bar is going to be your moment of x over the mass. Okay? So again, just check these off. Main thing you got to know is you got to be able to find your boundaries, and you got to figure out what is top minus bottom. Now, I will say this. All of these formulas are for top minus bottom graphs. They're R sub x regions. Remember in 6.1 talking about R sub x and R sub y? Okay. These are for R sub x regions. If you have an R sub y, and we will work one, if you have an R sub y region, you're going to flip-flop these two. Okay? So for an R sub y region, this is going to be m sub y, and this is going to be the formula for m sub x. Okay? So you're just going to flip-flop those. And then, of course, it'll be right minus left. So again, the formulas that I gave you on your formulas page, those are for R sub x regions only. And then if you do have an R sub y region, you're going to have to flip-flop your m sub y and m sub x. Any questions? Let's try it. All right, so you have a lamina of a constant area density, which means the row is going to cancel out. Okay, anytime it says constant area density, homogeneous, row is going to cancel out. Density does not matter. Has the shape of the region bounded by the graph of y equals x squared plus 1, x equals 0, x plus 1, or x equals 1, and y equals 0. Now, everybody sitting in this room should know how to graph those. Yes? X squared plus 1 is going to be a parabola, and it's going to have a vertex shifted up 1. So there's your parabola. And then you have x is equal to 0. X is equal to 0 is your y-axis. X is equal to 1 is a horizontal line going through the x-axis at 1. And y is equal to 0 is your x-axis. So what region are we talking about? We're talking about this little trapezoidal region right there. Okay, so what's the first thing we need to know? What's the first thing y'all want to find? You want to find mass first? Okay, so m is equal to, and you can just go straight off your formulas page. Again, we're not going to worry about rho. So what are our boundaries going to be? You need x-axis boundaries. So we're going to go from what to what? from 0 to 1. And then top minus bottom. Which equation tells us the top? Which function tells us the top graph? Yeah, that's your parabola. So you're going to have x squared plus 1. Minus the bottom. What is the bottom graph? X equals 0, or y equals 0. So, I mean, you can write it in there, but it's not really going to matter. All right, and everybody in this room should know how to integrate this, yes? If we integrate this, we're going to have what? X cubed over 3 plus x integrated from 0 to 1. So basically we're going to have 1/3 plus 1, and the zeros are going to go away, so it's not really going to matter. And so we're going to get 4/3. So the mass is going to be 4/3. Okay, let's go with the next one on your formula sheet, which is m sub x. Big M, notice, sub x, which is going to be your moment. Boundaries are not going to change. Copy down your formula, plug in as you go. So you're going to have the integral from 0 to 1 of 1/2, and we're going to move that out front in just a minute. 1/2 times your f of x function, which is going to be the x squared plus 1, plus g of x. In this case, it's going to be 0, so it's not really going to matter. Times f of x again minus g of x again, which is 0, so it's not really going to matter, dx. Alright, so that's your setup, and again, all you're doing is copying off of your formulas page. Just remember that this is your f of x, and this is your g of x. Okay, does that help? Okay, let's take those two binomials, x squared plus 1 times x squared plus 1. Basically, it's x squared plus 1 quantity squared. You remember the pattern, square, double square. All right, so we're going to have, I'm going to make the 1/2 out front. Square, double square is going to give us x to the 4th plus 2x squared plus 1 dx. All right, so if we actually integrate this, we're going to have x to the 5th over 5 plus 2x to the 3rd over 3 plus x integrated from 0 to 1. So we'll have 1/2 times, put the 1 in, we'll have 1/5 plus what, 2/3 plus 1 minus all that's going to go to 0, so it's irrelevant. And then if you put all that in your calculator, what are you going to get? 14 over 15 is what I come up with. Okay? So it's algebra and a little bit of calculus, basically. So you got to be able to do the algebra. All right, the last thing on our list is m sub y. So let's do m sub y. M sub y says that we're going to do the integral from 0 to 1 again. Your boundaries are not going to change. And then you're going to have x times f of x, which is x squared plus 1, minus g of x, which is 0, so we're just not going to worry about it, dx. Do the algebra. So we're going to have the integral from 0 to 1, distribute your x, and so we'll have x to the 3rd plus x dx. Actually do your integration, so we'll have x to the 4th over 4 plus x squared over 2 integrated from 0 to 1. Plug it in, and you're going to have 1/4 plus 1/2, which is 3/4. Okay, so we have all the things that we need in order to find the centroid. We have our mass, and we have both of our moments. We have the moment with respect to x, and we have our moment with respect to y. So now, in order to find the centroid, because that's what the directions are asking me to do, find the centroid. In order to find the centroid, I need to know what x bar is, and I need to know what y bar is. Well, x bar is going to be m sub y over m. And we found out that m sub y was 3/4 over your mass, which is going to be 4/3. What do you think? What do you think it's going to be? 9/16. Good. And you can put that in your calculator if you need to. So y bar is going to be m sub x over m. M sub x, we came out to, what, 14/15? Over the mass, which is going to be 4/3. Do the math on that, you should come up with 56/45. Do that for me. 14/15. Thank you. That sounds better. All right, so X bar, if you put, of course, make it into decimals, you're going to get 0.6 and 0.7. So if we go back up there, remember we talked about last week, in order for you to find the center of that region, in order to find that balancing point, you would hope that if you have this little trapezoidal region sitting like this, in order to find its centroid, you would hope that it's going to be somewhere inside that region, right? Well, 0.6, 0.7. 0.6, 0.7 is going to be right in there. So it is actually inside that region. When you do these, hear me now or regret it later. When you do these and you come up with a centroid, make sure your centroid is inside your region. Because if your centroid is not inside your region, you've got it wrong. You did something wrong. Okay? So go back and check it. All right, so you think you can set this up? You got it? Try it. Try this one. So what she has done over there is very good. All right, so you have y equals x squared, and that is going to be your parabola. And then you have your x cubed, which we know is our S-curve. And you can't hardly see it, but there is a little bit of area in there. All right, so our mass boundaries are going to go from 0 to 1 again. And we did talk about in order to figure out your boundaries, if you can't look at this and tell what your boundaries are, what you're going to do is you're going to set y equal to y. So you have x squared is equal to x cubed. And then from here, you know that you can do the algebra. And then set each one of them equal to 0. And so you're going to get x is equal to 0 and x is equal to 1. So that's where your boundaries come from. Then to figure out which one's on top, which one is my f of x and which one is my g of x, again, if you plug 0.5 into both of these, whichever one is going to be the biggest, whichever one has the biggest number, that's going to be your top. So this is my f of x, and this is my g of x. And again, once you get that figured out, the rest of it is just plugging it into your formula, and you're good to go. All right, so you have your boundaries, 0 to 1, and then for your mass, it's just going to be top minus bottom, so we're going to have x squared minus x cubed dx. And then do the math. So integration is going to be x to the third over 3 minus x to the fourth over 4. integrated from 0 to 1. Again, the 1 is the only thing that matters here, so you're going to have 1/3 minus 1/4, which is going to give you 1/12. All right, m sub x. n sub x, the boundaries are not going to change. So you're going to go from 0 to 1, and then you have 1/2 times. Now, this is where it gets a little crazy, I guess, because what you're going to do is you're going to do f of x plus g of x times f of x minus g of x. Do the algebra first here, okay? You can move the 1/2 out if you want to, but do the algebra first. And again, this is a sum and difference, so when you multiply this out, you should get the difference of 2 squares. Okay, remember your algebra rules also. When you multiply bases with, or when you multiply powers with like bases, you add the exponents here. Okay, so x to the second times x to the second is x to the fourth, and x to the third times x to the third is x to the sixth. So be careful with that. Okay, integrate from 0 to 1. So you're going to have 1/2, and again, the 1's the only thing that's going to matter here. And when you plug all that into your calculator, you should come up with 1/35. All right, last one, m sub y. M sub y, you still have your integral from 0 to 1, and then you're going to have x times f of x minus g of x. Do the algebra. And then do the calculus. Do the math. And you should come up with, what, 1/20? Okay, x bar. To actually find the centroid, you're going to do m sub y over your mass. Do the math, and you should come up with 3/5. Y bar, you're going to do m sub x over your mass. Do the math, and you should come up with 12/35. And of course, to check, turn it into a decimal, and it does fall in between. I mean, it's like right there, probably not even that much up, but it does fall in the region, so we're good. All right, so that's an R sub X region. Are you okay with the R sub X region? Any questions whatsoever? If you understood how to do it in 6.1, finding the area, then you're okay. Okay. So let's do one that's R sub Y. R sub Y region, I know that this is an R sub Y region. Well, let me do the graph first, and then hopefully it'll be obvious. The one on the right, this one, x plus y equals 3, that's a straight line. And it has the x-intercept at 3 and y-intercept at 3. So it's here. Now, the x equals 9 minus y squared, you're not used to seeing that. X equals 9 minus y squared is a parabola, but it's opening backwards, and it's opening to the left. So the vertex is out here at 9, 0. And then if you come in, if y is 1, you know that x is going to be 8. If y is 2, you know that x is going to be 5. And you can go even farther. If y is 3, then you're going to get the 0. So it's going to be this one here. So what region are we talking about? We're talking about this region here. Now, can you tell me why this has to be in R sub y region? Why does this have to be an R sub y region? Why can it not be? Do what? Yeah, you have some of your area that's below the x-axis. So if you wanted to do R sub x, you could. It'd be a booger of a problem, but you'd have to have two different problems. One for above the x and one for below. So I think it would be easier to do the R sub y. So for mass, and again, mass is going to stay the same, except of course for your boundaries. For an R sub y region, you know your boundaries are C to D, not A to B. Okay, so because we're using y-axis boundaries. But the formula is the formula; it doesn't matter. How can you find the boundaries? What do you think? That's exactly what I would do. This is going to be what? X is equal to negative y plus 3, right? Now you have x equals and x equals. So you can set the x's equal to each other. So now what you have is 9 minus y squared is equal to negative y plus 3. Well, since it's a quadratic and I don't like dealing with a negative y, I'm going to move everything from the left over to the right. So we're going to have 0 is equal to y squared minus y, what, minus 6. And then, of course, factor it. So we'll have y minus 3, y plus 2. And so you get y is equal to 3 and y is equal to negative 2. There's your boundaries. Okay, another nice thing about this one being a right minus left is it's extremely obvious as to which graph is going to be on the right. Yes? So, this is going to be really my f of y. And this is going to be my g of y. Okay. So, let's go. We got 9 minus y squared minus the g of y, which is going to be 3 minus y, negative y plus 3, however you want to put it. I guess we'll be consistent. And then, of course, dy. Okay. So this one's going to take a little while longer. Just be patient. Again, with these problems, especially one like this, be patient. Don't rush through it. Don't give up. Don't say, I can do this and move on. Practice. Prove to yourself that you can do this. Okay? So come up with the function that I'm actually going to integrate, please. Tell me what it's going to be. Who knows? In other words, when I subtract these two binomials, what do I come up with? Negative y squared plus y plus 6. Very good. And then the integration for that is not so bad, right? We'll have negative y to the third over 3 plus y squared over 2 plus 6y integrated from negative 2 to 3. Now, one of our boundaries is not 0, so nothing cancels out. You got to go all the way through. Just deal with it. You can do it. All right, so let's do top minus bottom. So we're going to have negative, or the opposite of 3 cubed over 3 plus 3 squared over 2 plus 6 times 3 minus, go with the top, so we have the opposite of negative 2, please be careful with your signs, cubed over 3 plus negative 2 squared over 2 plus 6 times negative 2. Come up with a number for me on that one, please. 125 over 6. Okay, m sub x. Boundaries are going to be the same, so we're going to have negative 2 to 3. But tell me what the formula is. What is the formula for m sub x? This is an R sub y region, remember. R sub y region, flip-flop formulas. And of course, we're integrating y's, so it wouldn't be x times. What would it be? Tell me the formula. It's going to be y times what? Well, it's going to be what? F of x minus g of x again, right? And we already have f of x minus g of x. So it's going to be that negative y squared plus y plus 6 again. All right, so do the math, and we're going to have the integral from negative 2 to 3 of negative y cubed plus y squared plus 6y dy. All right, integrate. So we're going to have negative y to the 4th over 4 plus y to the 3rd over 3 plus 6y squared over 2 integrated from negative 2 to 3. And you know that this is going to reduce. So that'll make it a little bit easier. Okay, so let's plug some numbers in. Go down here. Again, we're going to have the opposite of 3 to the 4th over 4 plus 3 to the 3rd over 3 plus 3 times 3 squared, bless you, minus the opposite of negative 2 to the 4th over 4 plus negative 2 cubed over 3 plus 3 times negative 2 squared. Come up with a number for me. And I'm going to go ahead and set up m sub y. Now m sub y is going to be the 1/2 formula. So we're going to integrate, and you can move the 1/2 out now or later, it doesn't matter. Boundaries are not going to change. But we're going to have 1/2 times, and you're going to do, well, you're going to do the f of y. F of y plus g of y. So we're going to have, and then f of y minus g of y. All right, so that's the setup for m sub y. The algebra on that is crazy. I am just going to write it down then. So m sub y is equal to, I'm going to trust that you can do some algebra. So we're going to have 1/2 times the integral from negative 2 to 3. And when it's all said and done with, you should have y to the 4th minus 19y squared plus 6y plus 72. And then we're going to integrate dy. I mean, it's not hard. It just takes forever. So. All right, let's integrate. So we're going to have 1/2 times y to the 5th over 5 minus 19y to the 3rd over 3 plus 6y squared over 2, and of course that's going to reduce, plus 72y. And we're going to integrate from negative 2 to 3. Alright, when you plug all that in, so I did the calculus, all you got to do is the math. When you plug all that in, I'll leave it for you. First person that tells me and gets it correct, I'll give you a bonus point. But we can't do x bar and y bar until you come up with it. So y bar is going to be 125 over 12 over the mass, which is 125 over 6. And when you multiply by the reciprocal on that, you should get 1/2. So we know we're going to have 0.5 for the y. Anybody come up with M sub y? Let me change mine. Oh. What'd you get for decimal?
Negative 309.
Mm-mm. Shouldn't get a negative number. Mm-mm. 30.4. That's it. Who was that? Sabrina. Good job. Alright, so the fractional form is 625 over 6. The decimal form would be 104.17, 104.2, however you want to put it. Alright, so x bar is going to be your m sub y, which is 625 over 6, over your mass, which is going to be 125 over 6, and when you do that, you're going to get 5. So again, please check your centroid and make sure it's actually in the region that you're talking about. 5 on the x-axis and 0.5 on the y-axis is about right here. So we are in our region, so we know that if it's not correct, it's got to be at least close. Okay, make sure you check your centroid. Make sure you check and see that it is actually in your shaded region. Okay, the last thing that we're going to talk about in chapter 6, yay, I know it's been forever, is fluid pressure. Now, for those of you that are going into, in particular, mechanical engineering, or any of you going into mechanical engineering? Okay. This is important. Fluid pressure, civil engineering. Do we have any civil engineers? That's important too. Usually like when we were building bridges, civil engineers and mechanical engineers work together doing this kind of stuff. All right, on your formulas page, it's kind of nice to you because I gave you the formula. The force F exerted by a fluid of constant density P, or rho rather, on one side of a submerged region is, and your F stands for force. And you're going to integrate from C to D. What does that tell you? Y, it's R sub Y. Okay, so we're doing y-axis boundaries. Integrate from C to D, and this time you are going to use rho. Rho is your density. And the reason being is because we're now doing summations, and what effect does that density have as far as pressure is concerned on a material submerged in liquid. Okay, so density definitely matters. Okay, so we're going to have your integration from C to D, and then you're going to integrate of rho, which is your density, times h of y. Well, h of y is going to be the depth of your sample. How deep is your sample? Okay, so remember when we were doing splicing, I think it was 6 point something or another, 6.2, 6.3. But remember we would take out a little rectangle, or what we would hope to be a rectangle, and we said, now how low is this actually in work when we were doing it? And we did something like 30 minus y, or 3 minus y for the depth. Same thing here. Depth of the sample is going to be something minus y. All right? And then your Ly is going to be your length times your height of your sample. Basically, it's just the area of a rectangle, if you have a rectangle. If you don't have a rectangle, then you're going to have to play around with some algebra. And of course, you know dy is always going to be your height. So there's your formula. You just got to work through it and figure out what's what. Now, you know that rho, again, is density. For water, do you remember what density of water is? 62.5. Now that one, I kind of sort of need you to know, okay? If I don't put it on the test, don't panic because you should know it. The density of water is 62.5. If I give you any other substance aside from water, such as tonight we'll be working with some oil, I will give you the density of that oil. So, if we're working with any substance aside from water, I will have to give you rho. Okay, so let's work one of these. The first two that we're going to work are fairly easy, fairly simple. And then the next two are going to be where we don't have rectangular splices, and I'll show you what you're going to do. But as long as you have a rectangular splice, a rectangular sample, it's okay. It's not that bad. Do what? So let's go back here. All right, so we have a rectangular fish tank that is 5 feet long, 2 feet wide, and 3 feet tall. It is full of water. That's important. And the water weighs 62.5 pounds per cubic foot. What is that? It's your density. That's your rho. Find the total force, F, of the water on, and we're going to turn this into a two-part problem. One side of the tank and one end of the tank. Okay, so let's look at the drawing for part A first. Well, for part A, we know that when we talk about one side of the tank, that's the long side, okay? So we know that this thing is 3 feet tall, and we know that this thing is 5 feet long. So here's our tank. And we know that this thing is full, okay? So the water goes all the way to the top. All right, so in order to find the force that the water is pushing on one side of the tank, what we're going to do is we're going to use our formula. So force is equal to the integral. What do you think are your boundaries? No. 0 to 3. You got to have C to D. So we're going to have 0 to 3. Okay, look at your formula. Go off your formula. HY is the depth of a sample. So what sample are we talking about? Well, if we take a splice out of this, let's say it's this splice right here. How deep is that splice at any moment? How deep is that splice, that rectangle? Oh, well, we need rho. You're right. Because it is rho. 62.5. That's rho. Sorry. But now I'm looking at H, what is it? H sub y, or H of y. The depth of the sample. At any time, as I move that splice up, at any time, how can I represent the depth of that sample, that splice? 3 minus y. Very good. At any time, you have to agree with me here, okay? At any time, the depth of that sample is going to be 3 minus y at any time, okay? And since this is an integration, that's what we're doing. We're summing the volume, the pressure, the force of each individual splice on the side of that tank, and then we're going to add them up. That's what the integration is. Okay, so you have rho, which is your density, because it does matter. 62.5 times 3 minus y. All right, what's next? So now we have L of y dy. L of y dy is length times, it's basically your area of your rectangle. So what's that going to be? The length, what is the length? Times 5. And what is the height always in our integration problems? We talked about this last week, dy. And you got it. That is your setup. One more time. Rho is your density. Okay? Rho is your density. H of y is the depth of your sample at any moment. And then your L of y is L of y dy. L of y is your length. Dy is your height. Always. Okay? So, can you tell me what I can bring out front? 62.5 and something else. Multiply them together and what do you get? $312.5 integrated from 0 to 3. And we are going to actually integrate the 3 minus y. dy. Tell me whether or not that makes sense. Does it make sense that we're only going to integrate the depth of the sample at any time going all the way up? Everything else is constant. What we're trying to do is we're trying to figure out how much force is being pushed on that plate of glass at any time through that water. And that's why we're integrating the 3 minus y. Okay? Because that is your depth. Okay, the integration you can do. So we have 312.5. And then you have 3y minus y squared over 2. Integrated from 0 to 3. decide where I want to go. And the zero's not going to matter. So what do you get? What kind of pressure? What's the number that you're coming up with? Yep. 1,406.25. Okay, so now let's look at B. Let's look at the drawing for B. It should, well, let's figure it out. Your density is pounds per foot cube, and then your length is going to be foot. It's going to, yes, and that's going to, so that's going to be foot squared, so yes, pounds per foot. Okay, so B. The thing's 3 feet high no matter what, right? But now we're talking about the end of the tank. So now when you're looking at the tank, you're not looking at the side of the tank, you're looking through the end. Okay? And the end of the tank, it's 2 feet wide. So here's your setup now. Look at the difference in the area of those two. Do you expect this answer to be bigger or smaller? Should be smaller. Should be smaller. Let's figure it out. So the force on one end, force, is going to be the integral from what to what? What are our boundaries? 0 to 3. Still going to do C to D. What is your density, your rho? Not going to change. And then what is the depth at any time of your sample? 3 minus y. So that's not going to change. But what is going to change? What's it going to turn into? All right. Go from here. You can do this. What are you going to bring out front? 62.5 times 2, and you're coming up with 125. We're going to integrate from 0 to 3, the 3 minus y. All right, so we have 125 times 3y minus y squared over 2, integrated from 0 to 3. And again, when you plug the 3 in, so you're going to have 125 times 9 minus 9 over 2, 9 halves. So what are you coming up with? Very good. 562.5. And it can be foot pounds or pound foot, however you want to say it. All right. Questions on this? For that one. As long as you have rectangular shapes, as long as you have regular shapes, this is it. This is it, okay? So let's do one more that has a regular shape. But this problem's a little bit different because, look, make sure you read it carefully. And remember, as you're reading through this problem, remember all the components of your integral that you need. You need rho. You need the depth of your sample at any moment. And then you need your area. Okay, your Ly dy. So watch this. A square plate that is 3 feet on each side. That's not so bad, right? This is where it gets funny. Is submerged vertically in a pond that is 10 feet deep. The bottom edge of the plate is on the floor of the pond, and the top edge is parallel to the surface. So let's see if we can draw this. We know that we have a 3 foot by 3 foot plate. But this is a plate that is submerged 10 feet. The bottom of the plate is on the bottom of the pond, The top of the plate is 3 feet, of course, 3 feet above the bottom of the pond. But how deep is this pond? The pond itself is 10 feet. So let's start setting this up. Now, pay attention, okay? You want to integrate the pressure on the plate only. You want to integrate the pressure on the plate only. So what are your boundaries? 0 to 3. Why would you not integrate from 0 to 10? Exactly. If you integrate from 0 to 10, you're putting all this pressure right here, and the plate's not even there. Okay? We're trying to figure out the pressure, the force on the plate. So we're going to integrate from 0 to 3. Now, we are talking about water, pond water, but it's still water. So what is rho? Yeah. Now, let's draw our little splice in here. Because now what we need is we need the depth of our sample at any moment. 10 minus y. 10 minus y. That's right. Any sample on that plate will be 10 minus something. And you know y would fall between 0 and 3 unless you looked at the plate, right? Times what? 3, which is going to be your length, times what? dy, which is your height. And you got it. Okay? So if you're talking about something that is submerged, you have to pay attention, and that's why all those words are in there. It's not just fluff. You have to pay attention to how deep the plate is submerged. You have to pay attention to the depth of where each splice is going to be. And you have to pay attention to the actual dimensions of the plate itself. Okay? So everything in this problem is needed. And then the integration you can do. 62.5 times 3, you come up with 187.5. Yes? So if you actually integrate, what do you come up with? Anybody? Very good. Very good. All right, any questions on that? Do what? Well, we got 2 more problems in chapter 6, and they're fun. Remember last week when we talked about the conical shape? I think we called it a pool, because you could swim in it. But remember what we had to do when we had a cone and we did the slice? Remember the edges were not vertical, so we had to come in, we had to take that into consideration. Anytime the edges of your splice, the edges of your sample are not vertical, you have to come up with a formula. Just like what we did last week. We came up with the slope, y equals mx plus b, the slope intercept point of that line, and we used it. Same thing. All right, watch this. The ends of a water trough, 8 feet long, have the shape of an isosceles trapezoid. Important. Of lower base 4 feet, important. Upper base 6 feet, and a height of 4 feet. Find the total force, so we're looking for F, on one end of the trough if it's full of water. Okay? So that's important too. The fact that it's water, you automatically know what rho is, right? So I ask you this. I want to know the pressure that this water is pushing on the end of this trough. Just the end of the trough. Doesn't matter how long this thing is. Think of all the components that you need. You need rho. Do you know what rho is? Because we're dealing with water. Do you know the depth of the splice of the isosceles trapezoid? The height of the water is going to be what if it's full? 4 minus what? Y. Now you got to find the area for your sample. It's not length times width anymore because it's a trapezoid. But at any moment is the length of this trough going to come into play. Do we care about the length of the trough? No. It's irrelevant. It is irrelevant. So we don't need that. Now, watch this. When you start drawing pictures of irregular figures, in other words, anything basically that's not a rectangle, you have to have symmetry. Okay? Did you get that? If you have an irregular shape, if it's not a rectangle or a square, you have to have symmetry. So when this thing says that it's an isosceles trapezoid, what does that tell us about the two sides? Not the bases, but the two sides. They're the same, right? The lower base is 4 feet. So watch this. We're going to go 1, 2. And we're going to go 1, 2. The upper base is 6 feet, but we know that it's 4 feet high. So let's go 4 feet up. And then go 6 feet. So we're going to go 3 left and 3 right. So here is the edge, or the end rather, of our trough. And we'll go ahead and put our sample in there somewhere. Okay, so let's set up what we know. We know that force is going to be the integral of what? What are our boundaries? 0 to 4, because you have the height of this thing. It's going to be 0 to 4. And then you need rho, which is what? 62.5. And the depth of your sample is going to be what? 4 minus y. Now, L of y is what's going to be a little difficult. But we did it last week, so I think you should be kind of familiar with it. So the length of this rectangle, it's not really a rectangle because we're talking about the sample, okay? The length of this sample is 2x. So L is equal to 2x. You get that? It's symmetry. Y-axis cuts it right down the middle, so you have a half and a half, so half and a half. When you add those two sides together, you get 2. 1x. Length times width. Okay. Alright. 2 times x is 2x. Length times width. But x, length times width. Okay? X times x is 2x, yes. But the sides is not really a rectangle. So we need a different way to represent x. Okay? So I ask you, like I did last week when we were talking about the cone, what can you tell me about the sides? What shape is that? What figure is that? What is that, geometrically speaking? This side right here, what is it? It's a straight line. This side also, it's a straight line. Can you tell me the slope? Let's take the one on the right. Can you tell me the slope of the line? 4 over 1, or 4, either way. We're not going to go there just yet. All right, so now we know slope. Can you tell me where this thing is going to cross the y-axis? Slope-intercept form, y equals mx plus b. And if you don't want to use your slope to figure out where it crosses the y-axis, then you can use point slope, right? Because we know a point. What's a point on this line? 2, 0. So I mean, if you want to, you can use point slope. Or you can use your slope and you can count your rise over your run, and eventually you're going to cross the y-axis. Okay, let's use point slope. So we'll have y minus y1, which is going to be 0, is equal to my slope, which is 4 times x minus x1, which is 2. So we're going to have y is equal to 4x minus 8. So if you had a u-slope, where would it cross the y-axis? At -8. Okay. So if you had a u-slope, and that should make sense because you're going to go down 4, back 1, down 4, back 1, that gets you at -8. Okay. But I need a way to substitute in for x. I have y. What are we going to do? I don't need y. I need x. Solve for x. So x is going to be equal to what? Y plus 8 over 4. And that tells me what those sides are going to do. So now my length, which I'm going to plug into my formula, my length is going to be 2 times x. And I'd prefer to go ahead and do the math here. So you have y plus 8 over 2. And then, of course, your height is dy. Okay? So that's your setup. Anytime, listen to me, okay? Anytime you have an irregular shape, number 1, split the y-axis. You have to have some symmetry going on. Number 2, in order to find the edges of your sample, for example, we need to know this little bitty edge right here or this little bitty edge right here. It doesn't matter because we're going to multiply times 2. Think about what shape you're dealing with, okay? I'm dealing with a line. I need a different way to represent x. Well, you know y equals mx plus b, and you can figure out x there. And you also know point slope, if you want to use that one. Y minus y1 is equal to m times x minus x1. So you have ways to represent x. Once you have a representation for x, plug it in, do the math. This is L. This is L of y. So L of y is going to your formula right there. So anytime you don't have a rectangle, you have to figure out how to represent x. You're going to represent x by using the shape of your side. If it's a line, use your linear formulas. In a minute, we're going to do one of a circle. Do you remember the formula for a circle from 112? x2 plus y2 is equal to r squared. X squared plus y squared is equal to r squared. Do you remember that? You need to remember that. Okay. So the calculus part is the easy part, right? What can I pull out this time? 62.5, there is something else. 1/2. Do you see it? I can pull this half out. Yes. So 62.5 divided by 2 is going to be what? 31.25. Integrated from 0 to 4. Now, we're going to have 4 minus y times y plus 8 dy. Do the algebra. When you pull this out, what do you get? Negative y squared minus 4y plus 32 dy. So there's your algebra. That's just the full method. Alright, so let's actually integrate. 31.25 times, you're going to have negative y to the third over 3 minus 4y squared over 2, and you know that's going to reduce, plus 32y, integrated from 0 to 4. Good thing there's a 0 in there. So we'll have the opposite of 4 cubed over 3 minus, let's reduce that. Really? Let's reduce it and integrate it. It's already integrated down. Alright. So, once you get all that plugged in, you should come up with 2,333.3. And if you want to do the units, you can. It's not necessary. You know, we were talking about the units. All the feet are going to cancel out. It's just pounds of pressure. Look, because you're going to have pounds per foot cube. That's this one. And then this one has a foot in it. This one has a foot squared in it because it's area. So they're all going to cancel out. Because this is your length, your L, and this is your height, which is another foot. So all 3 of those are going to cancel out. Mm-hmm. Well, it's force. Okay, let's do one more. And then we'll be finished with chapter 6. Chapter 8, y'all. Chapter 8 is going to be so easy compared to this. Chapter 8 will go by quickly. And then chapter 9 will be grueling again. So it's kind of like a roller coaster. Chapter 12 will be the easiest chapter of all those. So if you can stick around for that, you'll be fine. Okay, so look at what we have. We have a cylindrical oil storage tank, 6 feet in diameter. Is that important? 6 feet in diameter is extremely important. The fact that it is a cylinder, is that important? Sure, because it tells us what shape we're dealing with. And 10 feet long, is that important? No. 10 feet long is not important. Why is it not important? Because it's lying on its side. If the tank is half full, that's important, of oil that weighs 58 pounds per cubic feet, that is your rho. That's your density. Find the force exerted by the oil on the end of the tank. That's why the length is not important. We don't care about the length because we just want to know the force that the oil is exerting on the end of the tank. Okay? So, if we're going to draw this, and I know that I have a diameter of 6 feet. 1, 2, 3. 1, 2, 3. I am going to line this up at the origin. to the best of my ability, of course. So, that's what the end of this tank looks like. It's a circle. The top of a cylinder, it's a circle. And I know that this thing is half full of oil. Okay, let's try to set this thing up. So force is going to be the integral. Where is the end of this tank feeling pressure, feeling force? Is it feeling any force at the top? No, not from the oil anyway. Maybe from the weight itself, but not from the oil. Where is it feeling pressure? From where to where? Yeah, -3 to 0. So there's your boundaries. What did we say rho was? 58. Now, if I take a splice out of here, now be careful with this. At any time, what is the depth of the splice? What? Because we're only talking about the pressure of the oil. So I don't care about the top of that tank. I only care about the oil. What is the depth of that splice? Not to mention the fact, can I take that sample of oil out of the oil? No, then we'll have a sample of air and we're talking about something totally different. What's the highest that this splice, this sample can go? 0. The highest this sample can go is up to 0. Once it goes, well, it's not brain surgery. Look, this is a sample of oil. Once it gets above the oil, it's no longer oil anymore. It's now air. We're not talking about air. We're talking about oil. So it has to remain in the oil. Where's the top of the oil? At 0. So at any moment, this splice, it can be what? What is the depth of the splice at any time? Very good. 0 minus y. Wrong color. Which of course is going to be a negative y, but whatever. Okay, now this is the fun. We got to figure out where L is. L is going to be 2x. But we've got to figure out a way to write x. What shape are we talking about? We're talking about a circle, and I just told you the equation of a circle. What's the equation of a circle? Equals r squared, but what is your radius? 3. Your radius is 3, and then square it. What are we going to have? 9. Now, does that look familiar from 112? X squared plus y squared is equal to r squared. Now, what variable are we trying to represent here? What variable are we trying to represent here? X. X. Can you take this and solve for x? What is x going to be equal to? Right? X is equal to, because you're going to move the y squared over, right? So that gives you your 9 minus y squared, and then to get rid of the square, you're going to square root, so you have square root of 9 minus y squared. Right now, you can never take square root of a sum of difference. Never, ever, ever. Okay, so what we got to substitute in L. L is y. Okay, so what is L? 2 times that. And so that's what we're going to plug in. And then, of course, your height is dy. So this one looks fun, right? What can we pull out? 58, yes, keep going. Times 2, and there's one other thing it may be a little bit hard to see. There is another constant in there. It's a coefficient. -1. So let's bring out a negative 58 times 2, which is going to be what? Negative 116. It's right here. Better. So we brought out the 58. We brought out the coefficient of the y that's not underneath the radical, which is a -1. So you have negative 58 times 2, which is the negative 116. Okay. Let's go back to Cal 1. Can you integrate this? You don't know how to integrate a product, do you? You don't know how to integrate, and of course if we write this, this is going to be 9 minus y squared to the 1/2, right? Don't know how to integrate powers because we don't have a chain rule and we don't have a product rule. But what do we have? U substitution. Can you tell me what U is going to be? So what is du? Negative 2y dy. But what do we need? We just need a y. So what are we going to multiply by? So we have our dy, check, and we have our y, check. So what we're going to do is we're going to multiply negative 1/2 times that negative 116. And then the integration. But now we have u to the 1/2 du. Are you okay with that? Are you okay with how I went from here to here? U is 9 minus y squared. That square root is represented as 1/2. Okay? So we have u to the 1/2. All right. At this point, everybody in here should know how to integrate u to the 1/2. Yes? So you have what? U to the 3/2 divided by 3/2, and then you know what we're going to do from there, right? We're going to bring that out. So 58 times 3/2, what do you get? 116 over 3? Okay. One other thing that I want to draw to your attention is the fact that normally, typically, 0 is our bottom boundary. This time, 0 is our top boundary. And that's going to throw some things off. So be careful with that. Because you know when you integrate, it's always going to be top minus bottom. Right? So, how do you want to integrate this? Do you want to change the boundaries, or do you want to just plug u back in? Sabrina, how are you doing it? Are you changing them? All right, so we'll change them. All right, so we're going to have 116 over 3. We're going to leave it as u, and we're going to change our boundaries in terms of u. So let's plug 0 into 9 minus y squared. What are we going to get? Plug 0 into y, and you're going to get 9. Let's plug negative 3 into 9 minus y squared. What are you going to get? Well, negative 3 squared is 9, and 9 minus 9 is going to be 0. And that gives us our 0 boundary on the bottom again. So that's good. Okay, so now, this is what we have. You have 116 over 3 times 9 to the 3/2, or the square root cubed, however you want to look at it. Square root of 9 is 3, 3 squared is 27, so 116 over 3 times 27, you should come up with 1044 pounds of force. And that, my dears, is chapter 6. Question. said, chapter 8 will not be that long. Chapter 9, those sheets, your chapter 8 formula sheet. So hopefully you do that. And hopefully the chapter 8 formula sheet will not be a fiasco like chapter 6 was. Okay, so your chapter 8 formula sheet should look like a whole bunch of trig. So don't even go there. Okay? Do not let the word trigonometric throw you off. Okay? This is pure formula substitution. It's no big deal. You trust me? Okay. You should trust me. I've never led you astray. I promise this is not that bad at all. At all. This kind of trig is going to be fun, though. It's not that bad. Okay. So let's talk a little bit about trig. So some of the stuff that you didn't get from whomever you had trig with. How many of you had Miss Doss for trig? How many? You had me. All right. Okay. What did y'all have?
I did trig.
You did, but in high school, so it's
Junior
ago.
high school,
Yeah. Oh, jeez. Okay, that's okay. This you'll need. You may need these unless you know them. This is the trig sheet that you should have gotten 113. This is your Cal 1 formulas page. Go on Blackboard and print those off. Hopefully you've already done that because I asked you to do it last Wednesday. If not, I don't know what to tell you. Okay. So, when we talk about inverse, go back to 112 for just a second, okay? And when we talk about inverse functions, we're not talking about the vertical line test anymore, we're talking about the horizontal line test, okay? So when we talk about the inverse, we're talking about the one-to-one functions and we're talking about the horizontal line test. Well, let's break each one of these inverses down. For the first one, you have the inverse sine function. Inverse sine function. Now, I want you to notice this, okay? This is one way to write inverse sine. This is another way to write it. Okay, we say y equals sine inverse x or y equals arc sine x. These are two different ways to write inverse. Typically, if I see arc sine, I'm going to turn around and write it like this. So if you see me going back and forth, that's why. I don't like this. Just personal preference. You may not like this and go to that. That's fine. I don't care. Whatever. Anyway, when we talk about inverse functions, you have to pay attention because of the horizontal line test. You have to pay attention to your domain and your range. These are your boundaries. Okay? So, when we talk about inverse sine, I'm not asking you to memorize this, but keep it in the back of your head. Okay? If you want to write it down on your formulas page, that's fine. They're not on there, but you can write it. The domain for an inverse sine, look at what we've done. We've taken our sine function, watch this. If we take our typical sine function, you know typically it goes from 1 to -1, and then what happens is, well, how do I want to do this? Yeah, we'll go this way. It goes like that. But if I draw a horizontal line, what happens? Because this is going from basically from negative pi to pi. If I draw a horizontal line, what's going to happen? It touches twice. That's a big no-no. When we're talking about functions, especially an inverse function, that's a big no-no. So what we're going to have to do is we're going to have to cut this thing. So we don't need that part, and we don't need that part. Now look, everywhere I draw a horizontal line, we're good. That's why your range changes from negative pi to pi to negative pi over 2 to pi over 2. Well, when we take the inverse of it, you're going to flip your axes. So now our domain is from -1 to 1, and our range is from pi over 2 to -pi over 2. You have to remember this. Have to remember this. Put it on your formulas page. I don't care. Okay, cosine, same thing. Just remember your range is from 0 to pi, whereas your range on inverse sine is -pi over 2 to pi over 2. Inverse cosine is from 0 to pi. Extremely important. Make sure you remember that. Let's go ahead and talk about quadrants. Your inverse sine, since we're going from -pi over 2 to pi over 2, you know that's 90 degrees and -90 degrees. You have to stay in quadrant 1 and quadrant 4. Okay? And then when you get to cosine, in cosine we're going to go from 0 to pi, so we're talking about quadrant 1 and quadrant 2. And then when we talk about tangent, this is one that I want you to remember for chapter 10. I know it's down the road, but you still need to remember it. For the inverse tangent, your domain is from -infinity to positive infinity, and that's for obvious reasons. It just keeps going. It's an asymptote at pi over 2 and -pi over 2. So this, as you get closer and closer, talk about limits again. We'll talk about limits again in chapter 10. As the limit of your inverse tangent reaches -pi over 2, it goes to -infinity. Same thing, as your limit reaches pi over 2, it goes to positive infinity. So remember that. Your range, again, is -pi over 2 to pi over 2. Okay, so those are your inverses. Please remember those ranges. Write them down somewhere and remember those ranges. Now, let's go back to, again, go back to 113, go back to trig, whatever your case may be. And let's figure these out. Some of these you can use your calculator, some of them you cannot. These in particular, you can use your calculator. Now, hear me now, or regret it later. And I tell my trig class this too. If I ask for an exact value, do not give me a decimal. If you give me an exact value, that means that your calculator is using pi. Is pi an exact number? No, because you would die before you reach the end of it. Pi is not an exact number. If you're using pi and you're using your calculator and you're coming up with a decimal, you rounded that decimal at some point. And so that's not an exact value. Now, if you use your calculator, that's fine. Calculators are different. I can show you how mine works. Those of you who have Casios, I think I can show you how yours works. But for me, for example, to do tangent inverse 1, I have a tangent inverse button. So what I'm going to do is I'm just going to hit second tangent inverse and hit 1. And it's going to give me 45. That's degree measure. That's not exact either. When I say exact, I am talking about radians. Oh, so you mean I have to turn my calculator into radians? No. When I want an exact measure in radians, what am I asking you to use? Pi. Pi is going to be in your answer. So when I use my calculator, I type in tangent inverse of 1. I come up with 45. My calculator's in degrees, so that's 45 degrees. Does anybody know the radian measure for 45 degrees? You can figure it out, yes, but flip-flop it. Because this is going to be over 1, so you want your degrees on the bottom. Is that what you said? You may have said that. Okay. So, what's it going to be? Thank you. That's what I want. Pi over 4. Those of you who know your units units circled really well, you should know your 45s, 30s, and 60s. And of course your 90s and zeros. And 270s. You should know all those. I mean, those are basic. Alright, so in your calculator, type in inverse cosine, or cosine inverse, whatever, of -1. What do you come up with? 180 degrees. But in radians, or exact measure, what is 180? It's going to be pi. Yay. Okay? Let's try this. Now, with these, you kind of sort of need to know your way around your right triangles. Okay? Negative radical 2 over 2. What is radical 2 always deal? Which triangle is radical 2 always dealing with? Your 45, 45, 90. So you know that that's going to be in there somewhere. If you want to picture your little triangle in your head, that's fine. But can you tell me what this is going to be? Sine inverse of negative radical 2 over 2. It's going to be negative pi over 4. Sine, what is that? SOHCAHTOA, what is sine? Opposite over hypotenuse. Well, that's kind of weird. Because in your 45, 45, 90, what do you have? 1 to radical 2. So something's going on. What happened? How did we get to radical 2 over 2? It's rationalized. And you have to know all of this in your brain in order to come up with this answer. So sine inverse of negative radical 2 over 2 is going to be negative 45 degrees. If you don't know that, use your triangle. It's a 45, 45, 90. 1 to 1 to radical 2. Sine is opposite over hypotenuse. Which is going to be 1 over radical 2. Rationalize, you get radical 2 over 2. That's true. In the basic sense. Basic. Okay, so negative 45 degrees is going to be what? What do we say? Negative pi over 4. Okay, so if you can work your way around the triangle, these are not going to be that bad. Most of them you can put in your calculator. Try it. Put in your calculator sine inverse and then do your radical 2 over 2 and see what it gives you. I think it gives you some crazy decimal though. And I do not want a decimal for these. I want an exact answer. Pi needs to be in your answer. Did it give you negative 45? Oh, cool. Alright, so on the test, if I give you some of these, try using your calculator, but if your calculator gives you a decimal, you're going to have to work your way around the triangle. Okay. Okay, let's go here. Do you remember how to do this and this? You can't use your calculator. I don't want you to use your calculator for this. Find the exact value without using a calculator. So look at what you have. Your argument of sine. Do you understand how you're reading that? You have sine and then it's argument. But the argument of sine is actually another trig function itself. It's actually an inverse. Okay? If you want to rewrite it. And look like that. Okay, so what are you going to do? Well, you're trying to figure out sine of what? Sine of what I do is I just let it be y. So watch this. Y equals, now I'm letting this be y, so I'm going to figure out sine of y. Okay. y is equal to cosine inverse of 1/4. But to get rid of the inverse, all I have to do is this. So I'm basically asking myself, cosine of what number, or what angle, is 1/4? But I don't need an exact angle. I just need to know what y is. Because I'm trying to figure out what is sine y. That's all I'm trying to figure out is what is sine y. Watch this. If this is y, cosine is what? Cosine is what? Adjacent over hypotenuse. But I need sine. What is sine? Opposite over hypotenuse. So, uh-oh, we have a problem. Because we don't know opposite, but we can figure it out. Okay? So x squared is equal to x squared plus 1 squared, which is 1, is equal to your hypotenuse squared, which is going to be 16. So x is equal to the square root of 15. Oh, well, guess what? It's going to be your opposite over your hypotenuse. So you get square root of 15 over 4. Don't give me a decimal. That's it. Just don't give me a decimal. So look, what do? Well, when I ask you to find the sine of something else, you got to find the something else first in relation to your triangle. I don't really care what the angle is because that's not really what I'm looking for. I want to know the sine of that exact same angle. So if the inverse cosine is 1/4, then what is the sine of that? I want to know what is the sine of cosine of 1/4, or inverse cosine of 1/4. So once you can figure out what cosine of y is going to be 1/4, adjacent over hypotenuse, all you got to do is figure out sine, which is going to be opposite over hypotenuse, and you got it. So it's radical 15 over 4. Try another one. This time we have secant of sine inverse of negative 1/5. So basically, again, let this be y. So we're going to look for secant of y. What is secant? What is the opposite, the inverse of secant? Yeah. The inverse of secant is cosine. Cosine is adjacent over hypotenuse. Flip it and you have secant. It's going to be hypotenuse over adjacent. So that's what we're looking for. We're looking for hypotenuse over adjacent. Okay? So look at what we have. Sine inverse, we have y equals sine inverse of negative 1/5. Well, so sine of y has to be negative 1/5. So let's go to our triangle. And let's say that this is y. Can your hypotenuse be negative ever? No. So opposite over hypotenuse. So what is y? Or, I'm sorry, what is adjacent? What is your other side? So you get 2 radical 6. So what is secant of y? I know that sine y is negative 1 over 5. So what is secant of y? And that's fine with me. I mean, if you want to rationalize it, you can, but I'm happy for that. So when it's asking you for sine, arc sine, or sine inverse of negative 1/5, basically it's asking you sine of y, sine of what is negative 1/5. once you plug that into your triangle and you figure out the other side, then you can go to your outside function, which is what's important. Because on the inside, your argument, all you're trying to do is figure out the other side. Okay? And the only reason why this is on here is so that you can understand the derivatives and the antiderivatives. So we'll work one of these and then we'll move on. Okay? Same thing. We have tangent of y. Tangent of y is equal to 3 over u. What does tangent mean? So you have 3 over u, right? Let's figure out the hypotenuse. And it doesn't matter which one you let be what. So your hypotenuse is the square root of 9 plus u squared. So what is cosine? And this is where I want you to go to your formulas. Look at your chapter 8 formulas. Notice where you have sine, derivative of sine inverse, derivative of cosine inverse, derivative of tangent inverse, and derivative of secant inverse. Well, I can bring that u out front, and you're going to have 1 over the square root of 9 plus u squared. Right? I can rewrite that as does that look familiar to you? Does that look like anything on that sheet? You can look at the antiderivatives if you want to, or the derivatives. So you can see how these derivatives and antiderivatives have been derived. These formulas that are on your formulas page are in terms of u. And that's how they derive these. Now, the proofs are in your book. If you want some good sleeping material, go home and read it, because they're all in there. And your book will prove to you how we go from point A to point B. But we can do this one too, but we're not going to. Okay, so 8.1 is just a review of truths. That's all it is, okay? 8.2, what we're going to do is the derivatives and the integral. And that carries us to the top part of your formulas page, okay, where you have the derivatives and the antiderivatives, the derivatives and the integrals. I want to show you how easy this is, okay? I want to show you how easy this is. Here are your derivatives. If you have to take the derivative of a sine inverse of u, plug the formula. That's all it is. It's a formula. Notice you have sine. This would look like something like this. Sine inverse of 3x. What is u? U is 3x, right? So literally, if this was f of x, f prime of x is going to be 1 over the square root of 1 minus 9x squared times the derivative of u. Because what did we say u was? Oh, smart. All right, so